Welcome you guys for the panel, which we will have great panelists here on stage. They will introduce themselves shortly to talk about large-scale infrastructures, lesson learned from networking. A few words before we can start. I used to call it networking too, but I think networking is not really the right term. Networking is not networking anymore when I'm looking on large-scale GPU, AI factories or clouds. It has become actually the scale-out compute infrastructure. That's what it is. Networking, in my mind, those are discrete components, a switch, a NIC or something, but this is not what we're building. And in order to run an AI cloud, AI factory in large scale, it's not networking, it's a full compute infrastructure or a scale-out infrastructure. So that's how I look on things. Infrastructure is going to become, or has become, a very critical element. And today in the keynote, Jensen discussed the scale-out compute infrastructure in very details. He presented co-packaged optics as a key element that will improve or reduce power consumptions and increase resiliency of a data center and so forth. There is a good focus on that infrastructure. That infrastructure is key for performance, efficiency, and what we can do and what we can run. Definitely as we're moving to the reasoning era where we need much more compute and so forth. So that's kind of my view. We'll hear views here from the panelists, but as we start, we want to introduce them in a random order. No, it's alphabetic on the last name. Omar?
Sure, great. Thanks, Gilad. Thanks for having me here. Hi, I'm Omar Baldonado, part of the Meta infrastructure team, specifically supporting the large-scale data center networking, which supports all of our AI workloads, including Llama.
And Nidhi?
Hello, everyone. Thank you for having me here. My name is Nidhi Shabal. I lead all of our AI infrastructure at Azure. And I describe my day job as just designing, deploying the world's largest data centers and the world's largest supercomputers for AI and making sure they run smoothly. So,
Dan?
Good afternoon, everyone. Good to be here. I'm Dan Lenowski. I run the data center networking infrastructure for Google, and that nowadays also includes the ML acceleration, since Gilad has said it's become such a key part of networking and really creating these, amazing supercomputers, if you will, together. But good to be here.
Thank you for joining. Peter?
Peter Solanki, CTO at CoreWeave. We build really, really large supercomputers and do a lot of AI training for our customers.
And Pradeep?
Thanks, Gilad. Thanks for having me here. It's really great to be here. I'm a SAP Chief Architect for Oracle Cloud Infrastructure. Focus on many things, but these days it's all been about AI infrastructure, and that's why I'm here.
Yeah, and thank you for joining us today. We prepared around 200 questions, just so you know. If there will be time at the end, we'll let you ask questions too, but we need to. No, we have only a few questions. And if you do want to ask questions or tell your opinion, we'll have time towards the second part. So the first questions, just to start to creating the elements of what we're going to discuss. In your opinion, and feel free to answer it, you can jump in. How did the data center infrastructure evolve, transitioning from the traditional data center to AI cloud or factory?
everybody's looking.
Everyone can jump in on that one.
Everyone jumps in. Well, maybe from the end here, I'll go. At Google, obviously, we've been at it quite a while, over 25 years of building warehouse computing, and started really, obviously, I think everybody did with, off-the-shelf components. And pretty early on, going on 25 years now, we started doing our own thing, building infrastructure out of, commodity switches using OpenFlow and SDN to control it and monitor. And, generally the structure was, growing in bandwidth, supporting online operations in terms of, continuous operation of hundreds of thousands of switches, millions of servers over time. But it was generally an infrastructure for distributed computing, and one in which any individual application was not a dominant one of any one cluster. It was really a combination. So that structure, what we came up with, multi-tiered, which I think is pretty classic now, of switches and eventually getting into the petabit range of scale for individual clusters, using optical switching also on top of that in order to achieve better performance and flexibility. Now, when AI has come in, it is quite a different beast. I think, as we've said, it acts, especially in a training sort of situation, as one large supercomputer, and the characteristics are quite different in terms of the burstiness, the amount of bandwidth that's required, the latency requirements are lower. It generally, again, is a different sort of less tolerant sort of application, and one in which we have had major changes to the way our infrastructure looks to fit with it.
And the thing that I like to add to that is, it's not that they're not tolerant just by nature. By the way, they are. The frameworks need to improve. I'll talk more about that later. Like, it's kind of intentional, right? When we build a supercomputer, unlike traditional hyperscale compute, your focus is we want to have redundancy. Like, I'm happy to throw away half of the network bandwidth to ensure the services are always up. If I tell one of my AI training clients that I'm going to throw away half of the interconnect bandwidth, but the redundancy, they'll tell me to, go somewhere else. So you kind of build it intentionally to max out all the components, and that puts a completely different pressure on both, the network infrastructure, but also your operations processes. All of a sudden, we don't have redundant links everywhere where we can just take one down and, fix it a week later. We need to stay on top of things, make sure everything is operating at 100% all the time, and that goes, all the way from the data center to equipment choices and also our operational processes and how we lay all this out and build it.
Yeah, I was going to build on that. Like, at least in Azure, the approach we took, we actually did not evolve or transition from data center designs like traditional data center designs. We actually started AI from a supercomputing design that happened to be in a building that was a traditional data center, like a Microsoft building. But our data center, our infrastructure choices started with what a supercomputer needed in terms of scalability, reliability, and we started there. And like, it's much later that we realized that as we started to go into scale, that was at conflict with traditional data centers, traditional commercial clouds. Like, Peter was mentioning all the operations, the redundancies and things. These are things we don't build into a supercomputer at the same level that you would do for your traditional CPU jobs. A simple example as that, right? We do not waste any power. There is no buffers built out. You use every megawatt. And megawatt becomes the currency, not the space. You're not optimizing for space. You're not optimizing for anything else, but just you're really trying to maximize how many GPUs you can fit in, what level of file systems you can have, what level of cooling you can have. So we actually started in some way reverse. We started off, what can we do to build a supercomputer? And as we started to scale, we were like, oh, operationally, this is so different from our traditional. So we now have to change all the operations to match what is required for AI. So in some way, we deviated away from a traditional data center from day one.
I think I agree with a lot of the stuff that's been brought up. Something different, just to help hopefully complement. A lot of our design processes have changed. We've now built several generations of supercomputers now, starting with 16,000 GPUs and 24, kind of going bigger and bigger. I would say that a lot of operations certainly, but even our design processes. If I look at the first 10 years that we were building our data centers, they were fairly separate. Like, someone could build the shell, someone could build the network, someone could build the storage, and it just everything sort of just plugged together. But you really weren't treating it as a system that was all designed like one large supercomputer. So I think we've gotten better with that over the generations, where we say, okay, now the connections amongst all of our infrastructure groups are much tighter, and they're also they allow us to go much faster, because the evolution of the generations in the AI factory is much faster than it was in our previous generations.
Yeah, let me add on to that. I totally agree with all of it. Almost all of it actually applies to Oracle Cloud as well. But I think one of the key things that I would actually highlight is the pace at which the industry is demanding infrastructure to be built, and that essentially drives a bunch of innovation around being able to, as you said, the design aspects, but really about how do you optimize the process. And some of this is actually boring logistics. How do we actually build, hundreds of megawatts in a single site? Well, suddenly you have logistical problem around having people to lay down the cables, variety of things that you generally not think about, and those suddenly become a big challenge, right? So, and operational side as well, it is very, very unique. And as Peter said, the goal is to maximize the power, maximize the throughput, and you kind of need to stay on top of it. And you also, in a different way, like, we customers generally look at the availability very differently. And as a result, we have also adjusted some of our posture. As an example, change management, which is a, pretty rigorous process in Oracle Cloud. We have very different mechanisms. In general, in the cloud, we essentially want to deploy small changes, but in a small drips, stretched out over due course of time. But that doesn't quite work for AI infrastructure. Rather, you essentially bundle a whole bunch of changes, take a bigger risk, but rest of the time, you really minimize the risk, right? And that really helps the customer workloads. And that way they can run the training workloads during the peaceful time, if you will. And then there's a one window where there's chaos, and they essentially tune the algorithm so that it takes a break, if you will, right? And that generally tends to work out better. So across the board, it changes operations, it changes the process, the velocity and the pace of build out is way higher, right? For a given, a gigawatt, if you will. So that really drives a lot of changes from a design and operational and logistics standpoint.
Yeah, there is even one more point, because if I'm looking on traditional data center in the past, you guys here built hyperscale infrastructure before AI. So those infrastructure included a lot of compute engines. But an AI supercomputer or AI cloud, it's a little bit different. Now suddenly, if in the past there could be one network fits all, now there is NVLink as a network, there is a scale-out network, there is a front-end network, there is maybe storage network. The architecture is essentially completely different. And what Omar said, I'm going to jump on that one, and that's going to lead us to the next question, which is the rapidly evolving things, right? You guys build AI infrastructure or building AI infrastructure for a couple of years now. But what do you think is the difference between what was designed maybe 3 years ago versus what we do today for AI?
Yeah, well, I think the most obvious is scale, right? I mean, to the point that Pradeep was making, it, you used to be able to treat some subset or even a single node as, okay, a unit. So you take it down, you service it, you do upgrades, whatever you have to do. Now, a good chunk of a data center may be dedicated to one job. And if somebody's running that job and it's going to take them weeks, they don't want to have a rolling set of changes go through. It has to be done, all at once and then completed. And maybe just to step back to one thing that we talk about at Google is how search and all the algorithms that were designed to scale in a distributed way were designed to treat the individual machines as cattle, meaning any of them can go away and you keep going because they're all stateless and so forth. And we moved into cloud, it's pets. Everybody loves their computer. They want their DR, their redundant set of HA. That's the classic model, and that's a little different for us. And I would say it's with AI, ML, it's moved to I have a flock of pets. The entire array needs to stay up and be healthy for its duration. So it's definitely a tougher thing. And over the last 3 years, these flocks have just grown and grown to the point where it is quite difficult to keep them running on a consistent basis, and maintenance as well as just repairs is a major issue.
I see.
Yeah, cloud was, to add to that, right? Cloud was always made for lots of customers with small jobs, right? Where AI is few customers with very large jobs, like everything about that fundamentally changes the way. I love the analogy that you used on, like, flock of pets. Like, you have to, like, really think about few customers that are going to have large complex jobs, and the lifespan of the infrastructure sees so many things. What was bought for training, high-end frontier training, now pretty quickly gets devolved into, like, I'm going to run a whole bunch of inference on this, and I need to move to the next one to build training. So even just the lifespan of the infrastructure you're building and all the algorithmic changes that are coming along with that, that is very, very different from, let's say, an SAP job that has predominantly stayed the same over a period of time, right? So that mindset shift that has happened from, well, I have lots of customers that can take lots of compute, but they're kind of agnostic about how it goes, to I have a few customers that are very specific in their needs, and their needs will evolve, but they need to, like, have that capacity in a very regimented way. That has been a new thing for us. And even the same customers, like, we work with some really large customers, and the way they designed the network 2 years ago for their supercomputer versus what they are doing now for the next 2 years, 3 years is very, very different, right? So things are evolving very, very quickly in this space.
Yeah, if I can build on some of that, another key thing that we see different is essentially the density. As you mentioned, the way I look at it is, at the end of the day, the customer workloads, just AI training workloads and inference workloads, really need very large amount of compute to be packed in a very small amount of physical space, so they can talk to each other really well, right? With high reliability and higher bandwidth, lower latency, all of that. That really means that if you think about the networking aspect of it, the more you can actually bring them closer, physically speaking, better it is we can do a job in terms of networking them together, right? And that drives a lot of changes. The NVLink certainly was, a key part of that. But even if you look at outside of it, if you look at the cluster network, whether it's Ethernet or InfiniBand, there's a lot of, energy on how do we actually bring a lot of compute close together. Liquid cooling is a big enabler in that, right? So, the GB200 plus liquid cooling certainly helps bring a lot of compute together, and NVLink helps a lot of bring together a lot of compute in a small physical space, and that has been a big change as well that we see with AI infrastructure.
Yeah, in terms of applications, I mean, Nidhi, you made a good point that things evolve very rapidly, even during the lifetime of a cluster. And when we 3 years ago, people were training LLMs on text, didn't really need a lot of storage and a lot of read bandwidth for data sets. Then all of a sudden, people switch to multimodal, and now their read bandwidth from storage like 10x or 20x's. And you need to build your infrastructure available to handle these changes that you can't really predict. So building topologies, building things that you can expand them if you have to, an application layer, supporting services, object storage, and so on. With that is really important. I think that's gonna keep changing. And also the technology backing this is 3 years ago, InfiniBand was kind of the only option you had to do these things, and now we have Ethernet, Spectrum X. The technologies are also evolving as more and more people come in and build these things, and it's not just 5 big companies and supercomputing centers. The technology is also becoming more accessible.
Okay.
I can take one pass, just maybe a little bit different, is the talking. I mean, I love the physical infrastructure and kind of the reducing the distances and being optimal with power. But one part that has really changed in our AI infrastructure is the software layers above. Mm-hmm. Our container placement algorithms are much more aware of the applications. Our logging, you'd think our logging was just just dump the logs. But now our logs are an intimate part of how we run large jobs for weeks or months, because we need to kind of restart and checkpoint that. Same thing with storage. Yeah. Storage used to be just kind of put stuff there and read stuff out, but now it's in the critical path of these different jobs. So I think the storage, debugging, placement, software, kind of all of that has really become AI aware, as it sort of at all the way up the layers.
So going and looking on the large scale, and looking at what are the key technologies needed to enable scaling to 100,000 GPUs. But even let's take it more than 100,000. It's like several hundreds of thousands, or kind of the path. We start talking about million GPUs in the data center.
I think the simple answer is a lot of power.
Yeah. Well, in the past, when someone looks to build data center, looking on the budget that you have, and you probably put everything on the compute side, and then if something is left, you may put something on network, and if there is really something that is left, you might put some storage, kind of in a sense. I assume that now it's completely different approach. So in your perspective, can we start with Pradeep here? We want to go to 1 million GPU scale. What are key elements that we need for that?
You just 10x'd it on us.
Yeah, exactly.
It was 100,000. Now it's a 10. Now it's a million.
Yeah.
You're
All
sounding just like a
that's
customer.
for next year.
Okay. Next on the roadmap.
Well, I think when I look at it, as energy is a huge part of it. When I think in many ways, 10x might look like, hey, it's just 10x more overhead, maybe 10x more people, 10x more buildings, 10x more power, whatever it is. But if you think about some of the dimensions, don't scale that way. Energy, as an example, in many ways, when you actually try to scale 10x, you actually hit a lot more problems than 10x, right? When you actually, let's say, you have a really giant data center, let's say it goes into gigawatts or whatever, then suddenly you're actually like, breaching a boundary where you're actually going into government regulations. You might actually impact the whole grid and the entire state or entire part of the United States or whatever it may be. And that really matters. When you actually have even a cloud-sized data center before AI infrastructure, it wasn't that big in one site, right? And that moves. When you go 10x, it's not 10x scale. We actually have to deal with a lot more issues, all the way from energy production to how do we regulate that? How do we actually normalize the energy coming into the data center? All of that needs to be managed. The second thing that, again, to me, from my perspective, it's not a 10x issue. It's actually more than that. It's essentially the risk associated with that. When you actually have a lot more footprint, let's say in gigawatts, suddenly you have two types of big risk. One is around availability, right? Where suddenly everything goes down. It's a huge amount of capacity that you lose. It may be due to a hurricane, whatever it may be, natural or other man-made causes. It's a big impact, right? And particularly as we move towards inference workloads, that becomes a lot more challenging because availability really, really matters there, right? A lot more. And also, there's a second type of risk, and again, it's boring logistical thing, but asset risk. When you actually have massive amount of accelerated compute sitting in a small area, when you actually talk about millions of GPUs, that is again a disproportionate risk as well. So I think in a bunch of ways, there's a whole bunch of technologies need to come in around networking, around cooling, and logistical aspects around building these out. But honestly, at the end of the day, there are also other issues that we need to solve: energy, and how do you handle risk, how do you handle availability, and so on. I think a huge part of this, to me, is around power efficiency of the underlying infrastructure itself. The more we can actually get there, the more we can actually make the networking efficient, power efficient, more we can make the GPUs power efficient, I think we can get there much faster.
Yeah, and I mean your comment about network being second place, that hasn't really changed, right? The customers still want the maximum number of GPUs, and you saying 100K on a slide and asking me for 1 million, that's pretty standard, I guess, to get that type of upsell. But customers still want the maximum number of GPUs, so going after power savings, after network topologies, how can there's latency sensitivities. We can't just move all the networking to some building over here, especially at this scale. So how can we optimize these things to scram the most GPUs out of the building? It's going to be super important. And I mean, you guys talked about that today with co-packaged optics. Going to be extremely interesting to follow that. And then going up the stack, software layer. Everyone who operates 100K plus GPU systems are going to develop a lot of tooling themselves on top of what their providers might offer them, right? And especially around debuggability, tracing, fault tolerance that doesn't exist out of the box, right? Like if you look at the question before, like what has changed in the past 3 years, like I liked your answer because like you guys have built so much stuff in Meta for your training jobs. But if you look at kind of vanilla PyTorch and like vanilla training frameworks and so on, there is very little has changed in terms of how to make this easier out of the box on a large cluster. It's very hard to debug things. The error messages makes no sense. You get a work NCCL timeout, and then you're kind of stuck there unless you build a bunch of custom things yourself. So anyone who's trying to attack this at scale has to do a lot of their own invention. And I would like to see some of that go back into the open source systems as well, so it's easier to get started with training, even above 1,000 GPUs.
Yeah, the reason that I mentioned million GPUs is because the next question is on million. Okay?
Yes.
And I'm trying to combine two questions together so we have time to get questions from the audience. But would the answer would be different if it's 100K or a million GPUs?
Yeah.
Yes.
Yeah.
Definitely. Because 100,000 for us, it fit within one region, and it fit within the one substation capacity. Roughly however many 100 megawatts or so, and so. But when you go to a million, then you start looking at again the utilities and like what's available at that scale. So it's definitely different. I think my take on this question is that I wish I knew exactly which key technologies. So I think what we've had to do is we have there's a lot of bets that are kind of going on in parallel to say, okay, if a million is going to be done this way, let's pursue this with this optic technology. Let's pursue this with this. Let's pursue this. Because you just don't know. The models are changing so much. We're going to have a million GPUs systems, but then what will the models be? So you just to kind of be pushing multiple streams of innovation.
Yeah.
Power certainly, but everything else too.
Yeah, because we already have 100,000 GPU system in a sense, right? And we're already seeing the several hundreds of thousands of GPUs. So million is not that far. It's like a year,
Still
2
pretty far.
years. It's really not that
But
far.
one thing to keep in mind, right? Like Omar is saying, 100,000 versus a million, you start hitting the power grid to its limits. I might be wrong here. I looked it up a while ago. The Hoover Dam, I believe, is 800 megawatts. So it's not even a gigawatt. And some of these numbers, a million, you are going to hit a gigawatt. So there's not too many Hoover Dams out there, right? So I mean, there are real limits, especially if you are going to try and concentrate in one place, which is somewhat ideal. Now, I think there's another aspect of this that has to do with higher level software as to how do you deal with that. And in many ways, some of the things that we've been doing at Google really do take into account that there is a hierarchy and a distributed nature that you have to the algorithm writers have to deal with, just because you're not going to get actually that sort of concentration in one place. But it's interesting because people, as they just scale, sometimes they come to us with requests. Oh, I need flat, million, or 2 years from now. It's like, you're probably not going to get that, and if you do want it, you're probably not going to have algorithms that'll work if they really needed that kind of flat bisection bandwidth.
Yeah, and I think that's where the evolution. I know we are all infra geeks, so we want to scale infrastructure to get to a million. I think one of the big technology swing we will see is in the algorithm side. Like, I don't think the current wave will just continue by adding more and more GPUs to a job. I do think we are at a point where we will see that inflection point come from the algorithm side, where we would use the GPUs more efficiently. I don't think this will be this linear, like let's keep throwing at it, because at some point you do want to have that efficiency and the cost points that drive that, right? How many people will be able, how many companies in the world will be able to afford 1 million? I think with the whole open source move and like more and more people being able to get access to tens and hundreds of thousands of GPUs, I do think the algorithms will get to a point where that linear scaling would not be required. I think we'll see much better algorithms. And I'm not saying that a million GPUs will not get to that point, but I do think there will be changes, not just on the infrastructure to support that, but in the application side, that we will get a lot more for that million GPUs than we get today on our roadmap. So,
well, you heard earlier today, the more you buy, the more you save.
yes.
And I mean, your point was really good. I was going to get there as well, right? Like a million GPUs, doesn't necessarily have to be in the same campus. I mean, I'm
Exactly.
sure everyone would love it, but it's really hard because of the physical limitations. So if we can stretch, the top layer of our networks over multiple regions, this is actually a lot more achievable. There needs to be application layer protocol changes. You can't just run like Roki with PFC over several miles, but there are things we can do there to make that work.
Yeah. It was the more you buy, the more you make. I think it kind of fixed that point.
The more you save.
I mean, we won't get a discount?
Yeah.
Yeah. Oh, great.
Yeah, I jumped to the million GPUs just to say one more thing. Million GPUs not necessarily would be in a single place, a single data center, right? It could be spread across multiple sites. And if that's going to go in multiple sites, then mentioned there is a good amount of software that needs to be developed in order to do that.
Yeah.
Yep. Practically, I think that's really the best way to actually grow to million GPUs. So I totally agree. I think the software is essentially the way we are going to conquer that part of the world, right? So I think after a point, the scaling the cluster is really not the best thing for a variety of reasons, and then we essentially have multiple clusters, and they all like put together at a mega cluster at country level or whatever it may be, and then software essentially does that. And this is not unprecedented in the software world, right? If you look at outside of training or AI infrastructure, this has been done in other types of applications. I'm sure Google has done that. I'm sure Microsoft has done that as well. I think AI infrastructure needs to get to that point from an algorithm perspective.
And that is one of the challenges, I think, right now is that what is the algorithms, right? We think, as an infrastructure people, we think, it's going to have to change. And we've seen some of it at Google, but it's not everybody. But then at the same time, the algorithms for what is the best, inference, the best training, a mixture of experts, all these kind of different new techniques. If you talk to folks, there's not one opinion about where it's going.
Yep.
There's different opinions, and that definitely makes our lives challenging.
Yeah, and you build something, and finally there's something like, oh, this works distributed, and it's fault tolerant, and then someone comes out with some new optimizer or something that breaks everything, and then you're back at square zero.
But that's the joy of it.
That is the fun.
True.
That is the fun, I think, because the software, it's the whole stack, right? Because you look at the collectives, the parallelism models that Jensen talked about, that's at one layer. But then you also look at the job placement, you look at the transport, you look at the NICs, the firmware drivers that are and the capabilities that we have to work with you all on. And so all of that's going to come to bear. And the fun part is you just don't know exactly where it's going to happen.
And there's a little bit of time constants involved that are hard for all of us, right? To catch up to somebody's great, brilliant idea.
Like, that next year is kind of
Exactly. That just comes back to when you say a million GPU scale, I think there is a difference between running a fleet that has million GPUs, which I think, we're not very far from, versus running a job that has a million GPUs. Those are fundamentally very different challenges. And I think we're making progress on both dimensions, one faster than the other. And I think eventually we'll get to a point where there will be some momentum shift that will happen where you don't need that many GPUs for a single job. You'll still have fleet that is really big, but it's not for a dedicated single job. So those two vectors are different vectors, and the optimizations are different.
Can I share one story on this just to make it? It made it really real for me because I went to go visit one of our data center regions recently, and I've always been looking at the logical diagrams, and the logical diagrams were like, oh yes, here's some blocks here, and then they're networked over here, another set of blocks.
There's a thick line.
And there's a bigger line for the network, and they kind of all go together. And then I realized what I was looking at were not racks that were being networked in some sort of tiered architecture. I was looking at campuses, and each of the slots was a building. I was like, wait a minute, this is like fractal. Like I'm now seeing campuses being networked with buildings, and how are they all going to work together? So actually going to our physical site, it was very grounding to just see, okay, wait a minute, all those logical blocks are actually separated by distance. The team on site said, we'd love to dig you more fiber, but it is cold, and we can't dig in the ground because the ground is frozen. I was like, okay, this is some real physical.
Yeah, this is interesting because I
here.
think we've gone from an infra team to now really thinking about how quickly can you dig tunnels? How quickly can you get, I don't think I've cared about the winters in Wisconsin more than I do now, just because it drives a construction schedule, right?
Exactly.
So
And the weather.
yeah, it's or like, oh, somebody couldn't get into this data center because there is a winter storm going through. So I think these are the kind of things when you are running at that level of scale that you didn't think about before. So they're always pretty cool.
I think what we are trying to say collectively is that the best way to get to million GPUs for Gilad, for NVIDIA to cut up a GPU 10 pieces. And then that's a million. That's it. That was a joke, by the way.
Sounds like a great idea to me.
Yeah, now there are, different infrastructure, different AI workloads, right? Training is looked as, this is where I spend money, and inferencing looks like this is where I make money. In your opinion, can a single infrastructure support both workloads, both training and inferencing? Do we need build separate? What do you think?
Yeah,
Who's gonna go?
I guess I can start. Like, I think we had a hypothesis in the beginning of our journey, I guess, that AI training and inference will have divergent set of needs, right? And we were very focused on like, okay, the AI training, single large cluster in specific locations that are, and there is truth to that, but the reality is when you have a customer, they want to do training on the latest generation, but then they want to do inference on the systems that they have bought, right? So there is definitely a lot of fungibility between infrastructure over the life cycle, right? You do want to make sure that the infrastructure you're buying, either as an end customer, as a cloud service provider, can run both workloads, right? Now, there are sometimes nuances, right? You do want inference needs to be globally present. Inference needs to be closer to the users because of latency requirements. But just from a pure efficiency point of view, at least we do see, to the extent possible, we want to have things that are fungible, that can run both training and inference. And again, training is also not one single job, right? There are trainings at different levels. And to that, I would say, yes, there is frontier model training. Very few customers do it. Maybe that's a very unique thing. But everything else will be pretty fungible. At least that's the hypothesis we are running with right now.
Yeah, I would agree with that. And what is training also changes, right? You
Yes.
take inference as part of training, reinforcement learning, all of those things. Like the definition of training also changes all the time. And same for some with inference, with test time compute, and you add in CPU compute in there as well these days. So trying to build something just for this thing, the same thing with the question like what changed in the last 3 years, you're going to be sorry, you're going to end up rebuilding more than you should. And you also want to maximize your kind of footprint, your spend as much as possible. So if you have a lot of inference demand, right, all your dedicated inference compute is used up, you want to be able to burst into your training compute, maybe not preempt, your big pre-training runs, but research jobs and so on, you might be okay preempting, so you don't have to increase the latency user requests. So having that in both your compute layer and how you build your scheduler and so on, so I can preempt less important jobs and replace it with whatever other type of compute I need, not just another training job, but also inference, is super important.
Yeah, I think this is something that's also evolving, as especially as a cloud provider. Obviously the training, it's a lot of demand on units, and certainly those folks who are in that space and have been, starting to serve more and more, want to be able to make this trade-off and not have that infrastructure that they bought go idle either between training or because there's not enough inference happening. As things get more mature and more, hopefully, money is made, if you will, in terms of inference, I think some of the requirements that Nidhi was talking about in terms of edge, being closer to edge, optimizing for cost, right? And especially as the inference, as Jensen was saying, gets more sophisticated, these are all important things. So I think at the moment, definitely fungibility is important and probably will continue to be important, especially like you say, off the frontier models. Not other than frontier might be separate, but generally over time, I think there probably will be more sort of distinctly inference sort of machines and configurations that are set up. But at the moment, it's fairly fungible.
Probably for all of us, we don't have one single infrastructure. We have fleets, right? When we have different things that we can leverage. And so when we build new, you think of Jensen's curves this morning, with a Pareto optimization, you're thinking like, well, where am I optimizing on inference? Am I optimizing on training? and then where's the trade-off. Certain new clusters we'll build will be optimized for one, others for inferencing. That is a change from 3 years ago, where our inference was largely, able to be contained pretty easily within single nodes, actually within our conventional front end network. But then as things are getting bigger and bigger, we're seeing inferencing change, and the requirements are changing. I don't think it's so simple as to say inferencing scale is the training of a year ago or 2 years ago. Maybe that's true from maybe a physical perspective, but even some of the memory things are different. And certainly the traffic patterns are different from an inferencing perspective. The whole pre-fill decode is much different than the regular parallelism of training.
Yeah, I can build on it. I think we look at it from enterprise customer standpoint quite a bit in Oracle Cloud, and when we look at our customers, instead of categorizing as the training versus inference, the way we look at it is there's certain types of customers and workloads that look for very large clusters that are like in some locations, as opposed to somewhat globally deployed set of infrastructure, and that could be in many cases for inferencing, and there's like heavy requirements around latency, as well as data sovereignty, data residency, and compliance, so on and so forth. But also, some of the training is actually in there as well. So it's not that there are customers who actually want to do some type of training that's actually local in their countries, and that's actually quite important for those customers. So it doesn't cleave off very cleanly as inference versus training. There's a set of customer workloads that are perhaps inferencing centric, but then it's really about customer workloads and the nature of the data that they're actually using, right? And that really drives whether they actually want more of a global footprint or not. But apart from that, from an algorithm perspective, there are some differences, and clearly it does come up. The memory is a key difference. We see differences in the storage requirements as well. We certainly, from an infrastructure standpoint, we see differences in connectivity. You don't want to training; it may be fine if it's some remote location, but inference you kind of want to be in like closer to metropolitan areas and so on and so forth. There's a bunch of those. But at the end of the day, the compute itself and the networking may look somewhat similar, but the modalities of deployment, tend to vary. But it's not just purely on inference versus training, but it varies on multiple dimensions.
Okay. Last question from my side, and then we're going to open that for everyone here. We have several hundreds of people here, and each one of them wants to build their own 100,000 GPU system. They free some space in the garage, and they want to start
bunch of Sparks.
Exactly. So from your experience of building those infrastructures, what insight you have gained from your experience and how those shaping your next generation design, and what can you advise to other people that wants to build large systems?
We've been building TPU networks for quite a while, as well as GPU at Google, and one thing that TPUs have done for quite a while is scale, right? We've built up to 9,000 TPUs in its own dedicated ICI cluster networking, and that's done us well. And we see the GPUs coming on, going from 8 to 72 to 588, whatever that number was.
576, but who counts?
576. I'll give you an extra 12. But anyways, so this scale, I think, of the individual interconnect, if you will, I think that's going to be growing, and I think that has value. Now we've also seen as TPUs have outgrown a ICI domain that it's also important to increase the data center speeds and feeds. And I think in that front, the GPUs are kind of out front in our world compared to TPUs. So that's going to keep growing. And then I think, as everyone said, the flock or the ability to keep everything running and to diagnose it, to service it, to make it useful at the kind of scales that people want to go for very large scale, at least, is something that is extremely important. And without the sort of visibility, without the sort of techniques And even I'd say to build, right? At Google, we're used to incrementally building. Now you've chunked down a huge data center worth of things all at once. So these are the kind of changes that we've seen, and I think we're going to have to continue to evolve in order to keep up with the AI as we go forward.
Yeah. So this is very hard. That's what I've learned. Like, oh, we're going to build a cloud. How hard can it be? It turns out it was very hard. But it's also very fun. And it's not getting easier, right? I think we finally mastered all these interconnect things, and then now we're scaling to 1 million GPUs. Apparently, I thought it was 100K, but apparently it's 1 million today. And then Jensen is coming as well, all these new technologies, and we have megawatt racks. Like, things are only getting harder. So what are the things we can do to make it easier for ourselves? Those are kind of things I think about, right? So the stuff where we don't necessarily have to reinvent when we're reinventing 50 other things in the data center, like from one generation, maybe we can leave it the same. And then we expect all these things to fail, right? We expect things to break, and we as we talked about, it's good. Like, we push things to the max, so expect failure, but build everything in, both from how we service things, right? How can we replace something? How can we do quick disconnects for liquid? How can we do all these things in the physical side, all the way up to the scheduling? How can we expect failures and make our schedulers so that it doesn't impact customers? We can service things in different parts around customers' jobs versus impacting them and restarting them. How do we build all these things from the ground up, expecting this to always be pushing cutting edge, always be hard, and we're always going to deal with new things that we had no idea would even bother us a year before.
Yeah, I was going to say, I think it's clear, at least from my experience, that AI infrastructure is not for the faint of heart. Right. So the insight that I have really on this one is like, we're still in that cycle where I do expect we'll continue to grow 10x every 2 years in some dimension, whether it's fleet size, what number of GPUs needed for a single job. We are not off that bandwagon yet, right? So with that, you are constantly looking at what is the latest technology that is coming, and constantly, it's like every day, what's the challenge now? And like somebody would, oh, that'll never happen. Of course that'll happen, right? The key tenet, at least like what we try to provide to our customers, is around performance, reliability, scalability. And it's just like you keep those 10 and then say, okay, now if I have to 10x that in some dimension, how do I get to it? And once you feel like you have gone to that, you realize the next thing, like NVIDIA announces something else, and you are constantly. So I do think that the biggest thing in here is believing that your customers actually have needs that are in that 10x dimension, and the ecosystem is going to continue to innovate. So continuously acknowledging that, and continuously acknowledging that you will have to embrace that and move quickly. I think that is the kind of pace you've seen. It's like it's a startup that starts every day.
Yeah, the pace of change from the infrastructure side is very fast, but the pace of change at the model side is something 100%. Else. I think that's one thing. I think we had the panel last year. We were talking about this. My recommendation then and still, really know your models and what you're trying to do with them, and what performance you expect, and why. Why aren't you getting that? And go as deep as you can to understand that, both from a training and inference perspective, and then that will let you think about what parts of the new technology am I going to pick up. And what other possible model innovations are going to come down. The model space has actually really changed, because I actually, a lot of folks here, there's the open models, open source, a lot of sharing. We hit 1 billion downloads of Llama. NVIDIA was talking about open sourcing a whole bunch of models today that were announced. And I think because of that open system, the disruption can come from anywhere. Someone can publish a paper, some startup can do this, and now you want to know, hey, how does that affect me, and how can I incorporate that into my models and into my infrastructure? So know your models, but I would say don't design your infrastructure too tied to one model. Give yourself the flexibility to understand how you can adjust, because you will have to adjust in the lifetime of any given solution.
Yeah, so the collective recommendation from all the cloud providers is that don't build your own clusters. Give us our money, we'll do it for you.
Leave it to us.
Yeah. So yeah, as seriously, I totally agree. This is hard business, right? So this is a very specialized type of infrastructure. I used to think infrastructure itself is very specialized, but the AI infrastructure is even more specialized. So if you're, a smaller company, dealing with AI, trying to innovate, you should keep yourself flexible, right? At least in the initial phases. I'll give a boring answer. You should keep your cash, spent in a flexible fashion. I'm sure your CFOs will tell you that. And you should essentially experiment. Use maybe multiple cloud providers, different hardware technologies, and see what works for you guys, right? So usually that gives you quite a bit of bang for the buck. And when you become really big, and if you actually want to be, hey, I actually want to get into this business, we are so big that we can actually put in the resources to gain the expertise to run this well, then you can get into the cluster building business. But I would recommend, the initial phases, be careful. Let us take some of the risks, if you will. So it's not just the money, it's also a risk-sharing mechanism. And my guess is that it usually works out for many of the smaller companies.
Yeah, I understood the same thing, by the way. So it was like, if you want to build the data center yourself, don't try. It's too complicated. Use the experts. I got the same feeling, but Omar, did you want to say something?
I say we're not a cloud provider, but my advice, I think, especially in the light of this, is know your models, because when you're going to run it on different clouds, you're going to want to know what sort of performance should I be expecting, right? And you see the roofline, the data sheets from NVIDIA, then you're going to want to know, well, what am I getting from the cloud? And then you don't want to stick at kind of the general benchmark, right? You really want to know what's my company trying to do with this model, and then how will that be parallelized? How will inference work on that? What should I be expecting? So, whether you build your own or not, know your models.
So that was my last question. By the way, is the comment for the million GPUs? Take 4 years back, I think 4 years, like the large systems were like 8,000 GPUs, 16,000 GPUs. Now we're 10x. We've done a 10x. I think next year there is discussion about a gigawatt of data centers. So now you're getting multiple hundreds of thousands. I think we'll get there, but let's see. We have several minutes. Happy to take questions from anyone here. Those needs to be polite questions, please. Positive questions.
Hello. Great panel discussion, by the way. Thank you for organizing. So my question is, even at 100K GPUs, if you have intermittent spiky workloads that occur at various times, right? How do you forecast that? How do you sort of like balance it out to prevent grid instability? And what kinds of workloads tend to cause those sort of spikiness?
The spikiness can happen really from any workload, to be honest. Even in training jobs, right? When you run your collectives, if you don't overlay computer collectives, or when you checkpoint or restore from checkpoint, like there's many phases there that will give you spikiness. So the software features in the Blackwell chip, you can have like super caps. Your UPSs could be part of it. So there are many ways to design around it, and like it's all solvable problems. But you definitely have to design it from the ground up and not just turn on your 200 megawatt data center and then you blow up the utility. Then you'll be in a really bad spot.
Yeah, I would just build on that. Exactly. Like, I think the spikes generally come from like large training jobs. Is where we have seen those things come up, and that's where we've spent time with like UPS, generators, and then finally getting into the Blackwell chip. And I think that's the best answer to how do you get to a GPU level. Now, the solution we have right now, which is like somewhat reducing the spikes in the GPUs, is great for a cloud service provider, but it's not necessarily the best from an environmental point of view. So I don't think that's the final answer that we will land at, but I think that's the right direction of like, how do we make sure that we can reduce the spikes at a GPU level? And then eventually we'll get to a place where we can figure out how we can do it in a more environmentally friendly manner, but that's the right way to do. So.
Yeah, thank you very much. Very insightful panel. And you're right, we should do more experiments. One of the questions I have is around container placement optimizations as to what we should look for when we are building some of these things, and not just like one type of provider, but multiple providers. So any insight on container placement optimizations as to what we should see for the next generation design?
I'm not sure exactly where you're coming from, but generally doing locality is very important for these type of applications. And I'm not sure of all the other cloud providers, but we at Google are certainly providing more and more of this as this has become more apparent that users need control over the locality of their jobs. They need to be able to know from some virtual level, nickel, collective, where are these communications going to come from physically, and then mapping that to the set of hierarchy of the network such that it is contained. So yeah, I think it is an important aspect of providing highest performances to get maximized locality in the placement.
Yeah, and if you go your question, I feel like touched a little bit of multi-cloud, and if you both go outside of a region, right? Like in locality within a region in AZ, you get topology and so on, get topology in Slurm, get topology in Kubernetes. Like the tools are already there for placing your jobs well. And then you go multi-region, and they're kind of is tools and Q, open source, multi-cluster, and then you go multi-cloud, and everything pretty much falls apart unless you invest heavily in building your own tooling. And there isn't really a good solution for it. I think as we see the open source progression, like looking at from Kubernetes side how Q has progressed with a multi-cluster, like more and more is going to come there, and then we're going to have to solve the storage piece. Okay, how do we deal with storage locality? Because you also don't want to pay $1 gazillion in egress fees and fill everyone's internet pipes. Because you decide to run this training job here instead of over there. So there's a lot to be solved there. I think there's a lot of motivation to solve it. It's not moving as fast as I wish in the open source community.
Yeah, I think just practically also in terms of locality, just know when you leave a scale-up domain, know when how many switch hops you're going to be hitting, and then just say look, is this within rack? Is it within row? Is it within building or pod? And that's what we've had to do for our own container placements.
Yep.
Thank you for an excellent panel discussion. Mike's live. So in the keynote today, Jensen mentioned both InfiniBand and Ethernet. So as you're building out these massive clusters going from 100K to even 1 million GPUs, how are you guys thinking about InfiniBand and Ethernet, and are you also tracking the work of the UEC, the Ultra Ethernet Consortium? Thanks.
This is our favorite topic.
Exactly.
We were actually having a discussion before we sat down on should the IB people sit down together, the Ethernet people sit down together, confused people sit together, or
We just mixed and matched so that we can protect each other.
We got a little bit of an IB crowd here in the middle.
Go ahead, IB first.
I would start with I think there are a couple of things. One, we are in the middle of evolution, right? Like we were just talking about, we started off with a single job needing 10,000 GPUs to a single job needing 100K GPUs. Those are very different network requirements versus a fleet that you are running at 10,000 GPUs or 100K GPUs or 1 million GPUs. When you are looking at a single job, and even the nature of the job would define whether you are looking for a backend network that can do InfiniBand primitives, or you can do Ethernet, or you're looking at Ultra Ethernet. I would say at this point, it is safe to say, maybe I'm speaking for everyone, everybody is looking for all options. I don't think anybody would have, I'm only affiliated to X, Y, Z, right? I think we all have to look at all the emerging technologies, including the Ultra Ethernet side of things, and just really think about what is the benefit at the end of the day for the end customer when I think about rolling that technology at scale across all of my data centers. So I don't think anybody is tied down with one technology. It is all in service of performance, reliability, scalability, right? So it's safe to say, at least from us, that we're all looking at everything that comes on all of these protocols and saying, where should I have specialized networks, and where do I need to go towards more commoditized networks, and what are the benefits and trade-offs of that?
Yeah, there's never been.
So for this will be the last answer. Sorry, we have 5 seconds, and there's another session coming in. So I want to thank all of you guys, Dan, Omar, Nidhi, Peter, and Pradeep. Thank you for joining us. Thank you for you coming.